Hello everyone, I'm Norman Wahlberger. We've been talking about how to set up fractions, and in this final lecture in this series, I want to kind of give an overview, have a bird's eye view of how fractions fit in to the problem of number systems more generally. This is quite an interesting topic, I think, that is important for primary school and high school teachers when you're teaching young people. So we're going to be interested in the relation between fractions and other number systems. Now there's a standard story here that undergraduates are taught. And it goes something like this, that we have various number systems starting in complexity with the natural numbers, and then extending to the bigger set of integers, and then there's the set of rational numbers, extended then to the set of real numbers, and then to the complex numbers in a two-dimensional fashion. So this strip of 5 consecutive number systems is really at the heart of modern views of numbers, which is not to say that there are not other number systems as well. Certainly you can also consider extensions of the complex numbers, things called quaternions and octonions. And then there are a whole range of other kind of auxiliary number systems like finite fields and other things too. But the landscape is more or less dominated by this string here from the natural numbers to the complex numbers. And the whole thing is captured by this one picture. Picture showing the real line, which is the continuum. So that's modeled by the real numbers in the modern story, and then the extension of it in the two-dimensional setting to the complex numbers. The fractions, which we've been talking about, they don't appear usually explicitly as a separate thing. They're usually sort of subsumed with the rational number framework. Now, there's a lot that's problematic with this. If you've been watching other of my videos, you will know that I have a lot of objections to this whole story. I object to the use of infinite sets. I especially object to real numbers. So let's quickly actually make explicit, right? The real numbers are just a fantasy that are not supported by actual computational reality. And that is the way it is. But that's not to say that the complex numbers can't be supported. So once you get rid of the real numbers, then you can build the complex numbers as a quadratic extension of rational numbers, and then these higher ones also. So this thing doesn't break this sort of natural sequence, but it does bring everything down to an algebraic level where infinite processes are removed. But there's other objections that I have because I don't believe in infinite sets. And I also think that it's wrong to consider these number systems as embedded in each other. So I would much rather that you think about number systems as being separate. Okay, so let me further adjust this. So I don't like this inclusion here. I don't like this inclusion, this inclusion, this inclusion, this inclusion, this inclusion. I would rather think of all of these things as being separate. So you can create a system of natural numbers and a system of integers and a system of rational numbers and so on. But when you do that correctly, they are actually separate kinds of things. They are different kinds of mathematical objects. And there's relations between these. So there's, arrows connecting these various things, but it's really a case of having separate number systems. That makes it clear that it's not so crazy to have other number systems, because once you're agreeing that there's actually a whole range of different number systems, then what's to stop you from having yet other things, other systems in this big landscape of possible number systems? Okay, so the usual story of numbers is, in my view, fraught with logical difficulties, having to do with the non-existence of a real arithmetic for real numbers, historical confusions, and orthodoxy. So the orthodoxy is omnipresent in modern mathematics. Just undergraduates are told to memorize these things, and they just repeat them over and over again until it's sort of automatic. And they don't even really appreciate all the difficulties. But what about the historical confusions? That's a separate issue that is really worth thinking about. So to understand the historical difficulties, let's zoom out a little bit and just think about numbers in a very naive, all-embracing fashion. What are numbers good for? So numbers are good for two things. There are two primary uses of numbers. One is for counting, and the other is for measuring. And these are separate activities. They are quite different in character. When it comes to counting, it's a discrete kind of thing. And in a very simple-minded way, we can count a number of objects of a certain kind by making marks on a page. So a bunch of, say, vertical strokes will capture the size of some set or collection that we're interested in. A slightly more geometrical way of doing the same thing is to represent the objects with little squares arranged in a rectangle. That's a kind of a nice way. So here's two ways of representing what we usually call 4. But in fact, words and symbols for numbers are not really necessary for this kind of thing. So we can do operations with these kinds of numbers. For example, here's how you can add numbers. You just sort of concatenate them. Or at the level of rectangles, you just juxtapose the rectangles. And if you want to do multiplication, well, you can do it this way. You can say, what we could call 3 times 2 is, there's a copy of that 2, and then there's another copy of that 2, and then there's another copy of that 2, 1 for each of the strokes at the beginning, and then we put them all together and we get that. Geometrically, with the boxes, something similar, but you can do it a little bit differently. So 3 times 2, there's 2, there's 2, there's 2. We put them on top of each other to form a box, and then we can count the number of squares. So this is counting. This is the realm of natural numbers and then ultimately integers. But it's quite different from the other important use of a number system, which is to measure something. Okay? And as the ancient Greeks realized, and this is an understanding that has been unfortunately really lost in modern centuries. If you want to talk about quantities which represent measurements, it is more appropriate to think about representing these things geometrically. Okay? For example, with line segments. This line segment is the result of some measurement. We've measured something and we've seen that its extent is this much. Even in a more sophisticated modern context, if you have some kind of instrument panel and you're measuring some quantity, maybe temperature or maybe voltage or something, ultimately what you're doing is you're reading off on a scale, and you could, if you wanted to, replace that scale with just actually a physical measurement that corresponds to where the needle is. So for example, suppose that we were primitive peoples and we had only a very rudimentary sense of arithmetic, mathematics, and we wanted to measure the size of this rectangle that you're seeing here, the screen, okay, this board. How could we do that? Here is a way of measuring this board. We could take a rope. So this is going back to ancient Mesopotamia. Surveyors used ropes. So let's measure the width of this thing. Okay, so I'll put it there. I'll stretch it out so it's reasonable. Okay, I'll put my thumb there. There is where my thumb is. And now I'm going to cut it. All right. So now this string, or rope that I've just had, is now a representation of the width of this thing here. So I could take this with me. I could wrap it up, store it, move it somewhere else, and then I could show somebody else how long Norman's board is. And correspondingly with the height, let's do that too. So let's measure the height. There's no ruler involved. There's no prior number system. We're just measuring this thing. Okay, good. All right. So there is the height, and here is the width. So these two strings are really capturing the linear extent of this region. And if we were, say, interested in a field, we could do something similar with ropes. And it's important to realize that we are doing some kind of measuring here, right? But it's not with a prior numerical system. We're just really working at the level of basic segments. Now there's an arithmetic with these basic segments, as the ancient Greeks well appreciated. Addition is the analog of what we're doing over here. It's a concatenation. If we wanted to add these two things, well, we would just put them together in the obvious way, juxtapose them, and there would have a big string. Multiplication. That is interesting. So the ancient Greeks thought of multiplication of two lengths as resulting in an area. In fact, the product of this length, this width here, and this length, or this height here, would for them have been the area of the board. So that's reminiscent of what we were doing over here. Okay, it's reminiscent of it, but it's a little bit different in that we are now requiring a different set of units to describe the product. So for the ancient Greeks, multiplication was something that generated new or higher units. If you wanted to multiply 3 different lengths, well, then you would get a quantity which was really more like a volume. And this, of course, is consistent with a physicist's point of view. Physicists like to measure things, and there's units. And if you're squaring meters, you don't get meters, you get meters squared. Okay, it's very important in physics to keep track of the units. And the ancient Greeks were more inclined in this direction. So they thought very physically, and they thought in this sort of direct kind of way. And it's really important to appreciate that these are 2 different ways of thinking about what numbers are. Okay, so these days, this system over here dominates thinking, and this is just some kind of historical anomaly that's almost not appreciated at all. But from a logical point of view, this makes a lot of sense. It's consistent, and it's powerful. A big difference between the 2 systems is that in the counting world, there is a unit, just the single stroke or the single square. While in the segment kind of arithmetic, there is no natural unit. Okay? That means in that world, proportions between segments becomes more important. It's not a question of, absolutely how big is this segment. It doesn't much have a meaning. But the relative sizes of 2 segments, that has a legitimate meaning within that framework of doing measurement. Okay? So proportions play a bigger role in the ancient Greek way of thinking about numbers because they naturally arise when we're talking about measurements as segments where there is no natural unit. And Eudoxus and then Euclid in Book 5 have a theory, an arithmetical theory that deals with these proportions, and it's very beautiful. Commensurability also becomes an important issue. If you have 2 segments, A and B, a natural question is there another unit that you can find so that each one of these is a multiple of that one there? So that's going back to what we were talking about in the previous video on the GCD and the Euclidean algorithm, right? So in this case here, B is 2 times C and A is, say, 3 times C. So these 2 are commensurable, and here's a sort of a greatest common divisor geometrically of them. So once you appreciate that the ancient Greeks really had a legitimate point of view and that their system of representing measurements, quantities with line segments was a legitimate alternative to our discrete point of view, you see that there are these 2 pictures, and it's natural to ask, how can you connect them? So on the one side, we have counting numbers, which are really based on a kind of a discrete kind of mathematics. Technologically, it sort of corresponds to digital quantities. Over here, measuring corresponds to continuous things, like analog things. Okay? And this big dichotomy, this is a central dichotomy in mathematics between the discrete and the continuous, between the digital, and analog. And of course, the continuous is highly problematic because that's so much more complicated and difficult to get our heads around than the discrete in some sense. So the famous math problem 19 talks all about that. In some sense, you could say that, Eudoxus kind of has a mathematics for this side or an arithmetic for this side. Well, this really goes back to the Pythagoreans, who had this idea that everything was based on numbers, by which they meant natural numbers. Okay, so there's this tension here, and there's this really interesting question: how do we actually bridge this divide? Is it even possible? We are firmly over here. I mean, our number system is very much based on natural numbers ultimately, and there's a natural question: can we describe what's going on over here with our discrete digital kind of point of view? It's a very profound question. So if we're looking for a bridge from counting numbers to measuring quantities, then this is really going to require the notion of a unit segment, because crucially in the discrete world there is a unit. And so corresponding to that, we need to pick out a unit segment, which doesn't occur naturally. It's something we have to impose on that situation. So that's a kind of ingredient that we need in order to form this bridge. If we've done that, let's say we've decided that that particular segment corresponds to 1. That's our unit segment. Well, then we can get easily enough by juxtaposition segments corresponding to 2 and to 3 and so on, where I'll write things in this primitive way without the Hindu-Arabic system, just with a bunch of strokes. But how do you extend this kind of correspondence to cover more general segments? So we need to extend our natural number or counting arithmetic to be able to cover or deal with more general segments. And there's historically sort of 3 different ways of doing this. One is through fractions or rational numbers, which is what we're primarily interested in here. Then there's another method which is based on a place value system. We usually talk about decimal numbers, but you can also talk about binary numbers. In the old Babylonian times, they talked about sexagesimal place value numbers. There's a third approach here, which is a little bit more sophisticated, called continued fractions. I'll just put that down. I'm not going to talk about that, but it's important to realize that there's this other more elaborate, version of what's going on here as well. So now this brings us back to fractions and the question of how do we think about fractions, not as a theoretical tool, but as something that connects with the world of measurement. So this is a question of interpretation of fractions, of how you visualize fractions or how you give meaning to them, how you explain them to primary school students that you might be teaching. Okay, so a very pertinent question for educators. So the way I prefer to think about fractions sort of geometrically at the primary school level is to use unit squares to picture our counting numbers. So instead of having stroke, 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 etc., let's use these squares. Okay, so that's implicitly having a unit square involved. Okay, and to make things a little bit easier, let me magnify these squares so they're a little bit bigger. So this is just a magnification of this one here. So now the idea is that we can introduce new kinds of numbers geometrically by subdividing this basic square. If we subdivide it into 2 equal pieces with a vertical line like that, then we can represent the 1/2 of this thing as a new kind of number, and we could call that 1/2, or more primitively, 1/1/1. Here would be 1/3. Here would be 1/4. Okay, we subdivide the square into an equal number of pieces, and then we count how many pieces we have, and then we give that name to this little piece here. So notice that, strictly speaking, a prior Hindu-Arabic decimal number system is not really required for this. Like, we don't have to have symbols for 2, 3, 5, etc. We can just work with these sort of stroke, stroke, stroke representations of natural numbers, and we still can talk about fractions. Okay, so now we can combine these things. So here is, let me call it 1/2. Okay, there's 1/2, and here is 1/3. And so we can put them together. And then we're getting a rectangle which is, whose extent in the horizontal direction is no longer an integral extent. So it doesn't correspond to an integral number of squares. It's a new kind of number. So if this is our unit, which corresponds to the side of our square, then this width here is being represented by this sum of fractions, 1/2 plus 1/3. Okay, and we could use our fraction arithmetic to rewrite that as 5/6, or 1/1/1/1/1 over 1/1/1/1/1 if we didn't know any Hindu-Arabic numerals. So in this way, we get a new measurement, and we're able to measure more general segments by combining these kind of primitive fractional parts of a unit square. And this is a way of justifying, what a fraction is and why it might be useful. Of course, in other contexts, it's sometimes, educators like to use circle and pi and some, parts of a pi, like 1/3 of a pi or something. To me, that's a little bit more problematic because dividing a circle into equal number of pieces is just geometrically actually more subtle. So it's a little bit more direct, I think, to have this rectangular approach, but that's just my opinion. So if you were a clever primitive person and you were following this video, up till now you might think, well, that's pretty convincing. So now you've got this idea of subdividing a square. You've got these new, more general numbers called fractions. You can add them, you can put them together in however way you like. So you can get all kinds of lengths now, which are sort of not just multiples of a unit length to start with. That's great. So now surely there's a correspondence between this discrete number framework and this continuous number framework of the ancient Greeks. And you might, that's a very justifiable kind of thought to have. But remarkably, it's wrong, okay? And this is one of the great insights that the ancient Greeks had, Pythagoras and Pythagoras' school, realized that this correspondence is only a partial one, okay? And it has to do with the diagonal of a square. So if we take our unit square, okay, as before, and now we consider the diagonal. Let's call it D. Let's take this diagonal and put it horizontal so that we can compare it with the side. Now we have two different measurements. This is a direct geometrical quantity that we can obtain. So we can create a square with a straight edge and compass. So this is a constructible segment. But they realized that these things are not commensurable. And what that amounts to, in the language I've just been talking about, is that it's impossible to express this D by using fractions. So, let's say there's a half, there's a third, and maybe a quarter. Maybe these things add up to D. Or maybe we can get some kind of combination, because after all, we could divide the square into a lot of really small little equal pieces, so there's a lot of flexibility here. But it doesn't matter. No matter what we try, there's no way of exactly covering this D with a bunch of fractions. This was the great insight of the Pythagorean school. Now, the modern view of this, the modern statement of this important fact, is to talk in terms of a fictitious quantity called square root of 2. So one supposes that there's this fictitious quantity called the square root of 2, which is some number which has this miraculous property that its square is equal to 2. And then the statement is that this square root of 2 is actually not rational. Okay? That's not the right way of thinking. Okay? It's not the right way of thinking. The right way of thinking is that the arithmetic with segments is a richer arithmetic than the arithmetic with counting numbers. And in particular, this segment here, which you don't have to think at all in terms of the number square root of 2. It's a segment. This segment, which is incommensurable with this segment in the arithmetic of segments. And that's exactly why Eudoxus had to develop his theory of arithmetic with segments, and why Euclid placed such an importance on it in Book 5, and why John Keel, in this preface to Euclid, which I've quoted in my Sociology and Pure Mathematics lecture recently, why he emphasized this point of view as well. That a lot of modern, at his day, modern thinkers were unaware of this distinction between commensurable and incommensurable. And the way I want you to think about it is that the arithmetic with segments, going back to the ancient Greeks, is actually supports a richer arithmetic than we have with counting numbers. And to try to restate that in terms of real numbers and infinite sequences and so on is really a red herring, and it really confuses the issue. It's not at the heart of the matter. So you see the importance of the ancient Greeks' understanding here. Now, I just want to finish this lecture by also making contact with this second approach to bridging the gap between discrete and analog, which is through decimal numbers or binary numbers, or if you like sexagesimal, place value system numbers. Okay, where you're talking about, say, in the decimal world, 0.53492, etc., and each of these decimal points corresponds to a multiple of a power of 10. So these kinds of systems, these place value systems, depend crucially on a choice of base. Okay, you have to start with a choice of base 10, base 2, base 60, or whatever. Not so really with the fractions, as I tried to convince you now, right? We write our fractions with decimal expressions, but it's not really logically necessary. But for this system, it is logically necessary to specify a base to begin with. And very importantly, the arithmetic that you get ends up depending on the base. This is such an important thing to understand, right? That the things that you can say in base 60 are not exactly the same things as you can say in base 10, not exactly the same things as you can say in base 2. It makes a difference. So for example, let's say the fraction 1 over 15 in our usual decimal system. In base, okay, the easiest one is in base 10. In base 10, this is the decimal 0.0666, and it's repeating supposedly. In base 2, 0.0001, and repeating. In base 60, it's a finite decimal. It's 0.04. And I've just put this 0 here to specify that in base 60, the digits are between 1 and 59, okay, between 1 and 59. So this is a number between 1 and 59, or actually between 0 and 59. And there's only actually one digit, so it's really 4. Okay. So crucially, in the sexagesimal system, this is actually represented by an explicit number, which is a valid number in the old Babylonian system. While in base 10 and base 2, they are not, properly speaking, decimals that you learn in primary school. They are infinite decimals that have a repeating aspect. Okay? And the arithmetic of those is much, much more problematic. So there's actually a very weak link between fractions and decimals. There's connections between these two things, but it's not a very strong correspondence. Okay? So for a consistent theory, you need to extend to periodic decimal arithmetic. So to represent fractions in this world is actually a major challenge, and something I'm going to have to talk about in another famous math problem as to how to set up an arithmetic of periodic decimals. That's actually hugely challenging. Okay, so I'm just in this lecture trying to give you an overview of things, maybe with a historical emphasis, that fractions are a very important and useful theoretical tool, but for practical purposes, they fall a little bit short because they don't capture the richness of the measurement segment arithmetic of the ancient Greeks. And also because they are computationally just very cumbersome as you proceed with arithmetic. So we need to keep these things in mind when you're teaching fractions. It's actually a much more subtle thing. And more generally, mathematicians and educators should spend a lot more time thinking about the landscape of number systems and this very rich story, and trying to get our head around the right ways of thinking about this. In my next video, we're going to talk about another famous math problem connected with these things quite directly. We're going to have a little bit closer look at this diagonal of the square. So we're going to talk about how you arithmetically deal with the diagonal of the square. Hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.